Hello everyone. In this video we're going to delve deeper into solving linear equations to make predictions. Recall that as equations get more complex, you just need to remember the 3S system, right, for solving linear equations. Basically, the steps involved are simplify, separate, and then solve. Okay, so by simplify, of course, we mean simplify both sides of the equation as much as possible. You do that before you start separating, meaning before you start moving terms around, right? And then you go ahead and separate. That means take all your variables to one side. It makes no difference which side you choose. And then whatever side you choose, take the constant terms to the other side. And once you've done that, you go ahead and proceed with solving. So simplifying, of course, an expression will entail first getting rid of these parentheses using the distributive law, right? And then combining any like terms that may result after that. So we're going to distribute the negative 2 here, right? And we end up with negative 2a plus 6 plus 4 equals, and here we're going to distribute the 4. The first open parentheses means start distributing, and the closed parentheses sign means stop distributing whatever number was before the opening parentheses. So on this side, we end up with 4a minus 8. So on the left side, we notice now that we have two like terms. These two constant terms are alike, so we can combine them. So we get negative 2a plus 10 equals 4a minus 8. Now, we no longer have anything to simplify, so we're ready to separate. So we're going to move the variables to one side, constants to the other side. I notice the 4 here is a larger coefficient for a than negative 2 here, so I'll choose to move my variable terms to the right side. And recall, always remember the nice shortcut, change sides, change signs. In other words, you can move any term you like from one side of an equation to the other side, but as long as you just simply change its sign, okay? Because basically you're adding the opposite to both sides. That's why that happens. So the 4a is not moving, so it doesn't change signs, but the negative 2a is moving, so it changes signs and it becomes plus 2a. The 10 here is not moving, so it's not going to change signs. But the negative 8 is moving from this side to that side, from the right to left, so you becomes plus 8. So now we end up with 18 equals 6a, and all we have to do now is get rid of that 6 by dividing both sides by 6. So finally, we end up with 3 equals a. And as I've always mentioned, you should, anytime time allows, you should check it. If you want to do it, check it quickly, you can do so using a calculator. So just go ahead and, plug in for a in this expression, and in that expression, make sure you get the same result. Let's take a look at that. So here we'll just type in negative 2 open parentheses, and then remember for a we're going to substitute 3, so 3 minus 3 close parentheses plus 4, and then hit the equal sign, so we have that. And then on the other side we're going to plug in 3 as well, so 4 times 3 minus 2 close parentheses, hit enter. We do notice that we get the same expression on both, numerical result on both sides once we substitute a. So indeed, a equals 3 makes this equation true because you get 4 equals 4 at the end when you substitute it. So therefore, we've checked it and it is verified. So then we can write the solution set simply as the set containing 3. Next, we want to look at dealing with equations that contain with fractions. And the most efficient way of dealing with those kinds of equations is by clearing the fractions. The beauty of the multiplication property of equality is the fact that it allows us to multiply both sides of any equation by a constant of our choice, as long as we use the same constant as a factor on both sides. And that constant, when chosen cleverly, namely as the LCD of all the fractions on both sides of an equation, will help us clear all the fractions with one swift move, as you'll see. So here we have an equation containing fractions. We notice the denominators are 3, 6, and 4, right? So we find the LCD of these three numbers. One way is to just start writing the multiples of each number until you find the common one, right? So for example, you notice that the multiples of 3 are 3, 6, 9, 12, etc., right? So you write a few multiples of 3. And you do the same with 6. You have like 6, 12, 18, etc. And 4, you have 4, 8, 12. And we can stop now, because if you notice, we have found one number, namely 12, that is a multiple of each of those three numbers, and it is in fact the smallest such number that exists, right? So that's what we call the least common multiple of those three numbers. And once we find the LCD, we go ahead and multiply it on both sides. Remember, we can do that with an equation like so, right? So now also remember, that means we're going to distribute. So we're going to get So we're going to get 12 times 2/3 x plus 12 times 1/6 equals 12 times 3/4. Okay? Notice that we're just multiplying both sides by the LCD, and upon distribution, of course, the 12 will eventually have to be multiplied by each term, right? On both sides. And now we cross cancel and simplify. So here we notice that 3 and 12 reduce to give us 4 on the top. 6 and 12 will reduce to give us 2 on the top. And 4 and 12 will leave us 3 on the top. Now we'll carefully write down what's left. So as we can see, in the first term here, we're left with 4 times 2 times x, right? So that's 8x. Plus, in the next term, we have 2 times 1 left, right? So that's 2. On the other side, we have 3 times 3 left, so we get 9. See how nice that is? We took an equation that contained 3 fractions, and with a very, very clever and quick move, turned it into an equation that has no fractions in it. Fractions are fine, you should know how to deal with them, but anytime you get the opportunity to clear them and work with the much simpler whole numbers or integers, you should definitely take that opportunity and do so. All right, so we get 8x equals, we're going to move the 2 to the other side so it becomes -2. So we get 8x equals 7. Finally, divide both sides by 8, which is the coefficient of the unknown. And we end up with x equals 7/8. If there's no calculator handy, of course, you can always do it manually. 2/3 times 7/8 plus 1/6. We want to know if that's equal to 3/4, right? So first of all, we notice here that these two can leave us 4 down here. Anytime you have an opportunity to cross cancel and simplify, you should take that opportunity. So 7/12 plus 1/6, we're trying to see if that's equal to 3/4, right? So LCD here is 12, so that means we need to multiply this 6 by 2. So we get 7 plus 2, which is 9/12. We're trying to see if that's equal to 3/4. And 9/12, of course, if we cross cancel, is, right? 3 goes into 9 3 times, into 12 4 times. So now we finally end up with 3/4 equals 3/4. So we have verified it manually, okay? So that's pretty much the way you would approach a fractional equation. It always works out well that way. Now, one last thing I want to show you before we leave this problem is how to find this LCD. See, this method is pretty effective for numbers that are not too large, right? But if numbers are much larger, then you better have a more efficient approach, right? And that's what I'm going to show you now. Okay, so to demonstrate, let's look at a problem like this. Notice if you want to sit here and write a bunch of multiples of these 3 numbers, it's not going to be as quickly done or achievable as it was in the other case. So here is the way that you can do this more systematically. So go ahead and find the prime factorization of 24. In order to do so, just write 24 and draw a line and next to it, and start by, this is going to be similar to the factoring tree, but it's kind of like the more compact, more like mature way of doing it. So we go ahead and look for the smallest prime number that goes into 24. We know that's 2. We write it here. We divide and write the result on the right side, right below 24. And then we repeat the process until we get 1 on the right side. So notice that we can have 2 go into 12 again. So we can write 2 and divide, we get 6. Again, we divide 2, we end up with 3. And then finally, the only prime that goes, notice 3 is a prime number. So the only prime number that goes into a prime number is itself. And we get 1 on this side when we divide. Once you get this 1, the process is finished. Now you have the prime factorization of 24 right here. Notice 2 to the power of 3 times 3. We'll do the same thing for 20. So notice that we have 2 gives us 10, 2, 5, and finally 5, 1. So there is the prime factorization of 20, which is 2 squared times 5. And finally, we do the prime factorization of 15, which gives us 3, goes into it 5 times. So we write a 5 under the 15, and then 5 is a prime, so the only prime that goes into it is itself. We write that on the left side, and we divide, and we get 1, which we write on the right side. Again, once we reach the 1 on the right side, that's when the process ends, and we have the prime factorization on the left side. So 15 is 3 times 5. The really simple procedure you can use to find the LCM of certain numbers, which when it comes to denominators, the name becomes LCD, is to basically multiply the highest power of all factors, okay? So we multiply the highest power of all factors. Which factors? All the factors involved in these prime factorizations, okay? So the factors involved, notice we have 2, 3, and 5. So for 2, what's the highest power that you see? It's 2 cubed, right? Because remember, we're trying to get a number large enough where they all go into it. That's why we need the highest power, and that's why we need every factor represented, not just the common factors, because otherwise some of the numbers wouldn't go into it, right? So for 3, the highest power of 3 that we see in any of these factorizations is just 3 to the 1 or 3 itself. For 5, also notice there's no 5 there, but there's 2, 1 here and 1 here. But the highest power that we see is 5 itself, right? 5 to the 1. All right, then we multiply that. So notice that's 8 times 5 is 40 times 3 is 120. All right, so now we have the least common denominator as 120. So we can see that, for example, 24 will go into 120. 24 is this much of it, right? 5 times. So let's put it like this. Let's go ahead and multiply both sides by 120. Remember, because of distribution, you're going to end up multiplying 120 by each term, right? So we can save one step by just assuming that. And then notice here, 24 goes into itself once into 120 5 times. 20 goes into itself once into 120 6 times. 15 goes into itself once. And notice 15 goes into 120 that many times. So 8 times. So now the simplified equation is going to be 5 times 1 times x, so that's just 5x minus 6 times 1, which is 6. And on the other side, we have 4 times 8, which is 32. See how nicely that happened? We took that equation with all those fractions and turned it into a really nice, simple one with no fractions. So now we move the negative 6 to the other side, it becomes positive 6. So 5x equals 38, or x equals 38 over 5. Let's do a quick check of that on a calculator to make sure we didn't make any kind of error. All right, so remember, to check, we have to go into the original equation. So we're going to put 1 over 24, and we're going to multiply that by x, which is 38 over 5. And from that, we're going to subtract 1 over 20. Oh, gotta get out of there. Arrow. Minus 1 over 20. Okay, so we turn that into a fraction and we realize that yes, that is in fact what we get on the other side as well. So we verified that the solution is a proper one, and now we go ahead and write the solution set in this manner. We use this set notation with braces, and we put just the numerical value of the solution, so 38 over 5. You don't want to put x equals or anything like that. All right, and that's how. So this procedure is very fail-safe and it's very algorithmic, so it will give you the LCD in a very efficient manner every time. And no matter how large the denominators are, this works seamlessly and beautifully. Okay, so always remember, find the prime factorization of all the denominators. Then once you have the prime factored form of each denominator, go through, multiply the highest power of each of the factors that you see present, right? First, determine what factors there are. We see there are powers of 2, powers of 3, and powers of 5, right? And so therefore, we simply pick, of all the powers of 2 that we see, we pick the highest one, which is 2 cubed, right? Of all the powers of 3 that we see, we pick the highest one, which is 3. And of all the powers of 5 that we see in all the factorizations, we pick the highest one, which is also just 5. So we multiply that out, 120. The beauty of 120 is that it is the smallest number that all 3 of those denominators go into. All right, great. So as mentioned in our previous video, one really important distinction to make is the distinction between equations and expressions. And of course, if you recall, what we do with expressions is we simplify them. And what we do with equations is we solve them. So if we were to compare these two, notice here, there is no equal sign with an expression on either side. So this is just an expression. And of course, we're going to simplify it. This one has an equal sign with an expression on each side, so we actually solve it. So we want to go ahead and proceed with simplifying this expression, solving this equation, and then we'll compare the first step of the two problems. So the first one being an expression, I don't have the option of clearing the fractions. I have to deal with it. So basically, what I'm going to do is find the LCD, which happens to be quite simple in this case, right? Because these two numbers are prime. When you have two prime numbers, you want their least common multiple, just multiply them, right? So basically, we notice that we can simply think of this as 2x over 5 plus x over 3. Now we need the LCD, which is 15. And now what we're going to do is we're going to turn each of these denominators into 15, right? So for 5, we need to multiply it by 3. But remember, when you do something to a denominator of a fraction, you have to do the same to the top. So do keep in mind, the first thing we did was to find the LCD, which is 15, right? And back to this, remember, we multiplied a denominator by 3, so we have to do the same to the numerator. And for the 3, we have to multiply it by 5 to make it 15. So of course, we have to do the same to x on the top there. This way, we're multiplying by 3 over 3, which is 1, which is fine because you can multiply any expression by 1 without changing it. And here, we're multiplying by 5 over 5, which is 1 as well. So we end up with 6x plus 5x as the new numerators, right? Which we can combine. So now, in the end, we end up with 11x over 15. You may see this expressed as 11 over 15x. Now, when it comes to this other problem where we're solving this equation, notice we are still going to find the LCD, but we'll use it differently. Let me separate the two problems. All right, so we have 2/5 x plus 1/3 x equals 4/5. Remember, we're going to find the LCD again, which we already have, because on the other side, we don't have any new number. It's just another 5. So now we go ahead and multiply the LCD by each term, right? Remember, it's because of the distributive property that happens. And now we can cross cancel. 5 and 15 leave us 3. 3 and 15 leave us 5 on the top, and 5 and 15, 3 again. So now for the first term, we get 2 times 3 times x, which is 6x, plus here we have 1 times 5 times x, which is 5x, equals, on the other side we have 4 times 3, which is 12. So we get 11x equals 12. So x equals 12 over 11. We can check this manually, or at the very least we could plug it into a calculator, so as we have been doing. So let's go ahead and do that to save us some time here. So we plug in 12 over 11 in the original equation. Make sure we end up with 4/5 once we have plugged it into the left side. So we get 2 over 5 times 12 over 11 plus 1 over 3 times 12 over 11, right? And we want to make sure that that results in 4/5, right? Now we have that in decimal form here. If we click that, we can see that it is in fact 4/5. So we can check, we verified that it is the correct solution. So now we go ahead and let me bring this back up. Write our solution set as the set containing 12 over 11, like so. So notice, comparing the first step of both problems, we do the same thing. We find the LCD, right? However, we do very different things with that LCD. In the case of an expression, we can't use it to clear because there are no two sides we can multiply by the same number to keep the balance. So here we just have to use the LCD to actually find the common denominator and combine these two unlike fractions, right? Or rational expressions, if you want to be really precise about it. So we go ahead and find the LCD, which is 15. We turn both of the denominators into 15, and of course whatever we do to each denominator, we also do to the numerator. Then we combine those new numerators and we end up with this expression. So notice the outcome of simplifying an expression is an expression, right? Whereas the outcome of solving an equation is always going to be some numerical value, right? Unless, of course, you get into like some special cases where you either have no solution or infinitely many solutions. I'm going to show you a quick example of those so that our analysis of equations is not left incomplete. Remember that just because you see an equation, it doesn't mean you're going to have a solution. Here's an extremely simple equation that is not going to have any solutions, because basically if you just look at it, right, and not all equations that are not going to have solutions are going to be so simple to analyze. Sometimes you'll have to do some work to realize it, but with something like this, you can already see it's asking for too much. It's asking you to find some real number that stays the same if you add 1 to it. Well, that's impossible, right? If you add 1 to any real number, it's going to be one number larger, right? So, but let's say you didn't realize that and you started to solve it. So you go ahead and get the x's on one side and get the number on the other side, right? Uh-oh. Lost my whiteboard here. Here we go. So we get 0 equals 1. Notice this is what we call a contradiction. A contradiction is a statement that is always false, or basically something that goes against what you know to be true. When that happens, you know that the equation basically was asking for too much, for something impossible, right? So in this case, you say the solution set is empty. You use that notation. That's called the null set or the empty set. Okay? You can also write it like this. You know how the familiar set notation? You can use it, just don't put anything inside, right? That's the same. So this notation here, the two braces with nothing inside, and this one are saying the same thing. They're both called the null set or the empty set, right? Here is, and on the other extreme, you have some equations that have way more solutions, many more solutions than one. Here is a simple example. Okay, at the outset, it looks just like a regular equation, but if you try to solve it, watch what happens. Go ahead and get the x's on one side and the constants on the other side. You end up with 0 equals 0. Well, guess what? That's always true, right? This we call an identity. Notice the variable fell off, right? So here, when you get that, that means the equation was just asking for something so obvious, right? In other words, the equation is always going to be true. It doesn't matter, because look at what happened in the second step. We could have actually reached this conclusion right there when we saw you have something equals to itself, right? I just wanted you to go through and see how you'll eventually end up with a super simple identity where you have just one number equals itself, right? So, but of course, you could have made this jump to this conclusion right there at this step as well. Anytime where you get the same expression on the left side and on the right side, you can reach that conclusion, right? And what that means is, look, it doesn't matter what I plug in. If I plug in 0 here, I'm going to get 2 times 0 plus 4, which is 4. And of course, I'm going to get the same thing here, 2 times 0 plus 4, which is 4. If I plug in 1, I get 2 times 1 plus 4, which is 6. And of course, I get the same thing here. So you get the idea. Every real number, it doesn't even have to be whole numbers. Plug in a half, it's going to become true. Plug in pi, it's going to become true. Plug in the square root of 2, it's going to become true. So therefore, every real number is a solution of such an identity. So we say the solution set, not you, we say the solution set is the set of all real numbers, like that. Okay? So we can also write it as an interval. We can say negative infinity to infinity, like that. We want parentheses on both ends because you cannot include negative infinity or infinity as numbers because they're numerical concepts. They're not actual numbers, right? So this basically means all real numbers as well, right? So notice here, in this case, we have infinitely many solutions. That's the proper way of saying that. Sometimes people incorrectly say infinity many solutions. No, you don't use the word infinity in that way. If you're going to say a problem or an equation has infinitely many solutions, then you write it like this: infinitely many solutions. That's plural, okay? Like that. This one, of course, has no solution. So if somebody asks you what is the number of solutions of this equation, you can say 0, because you're not saying 0 is a solution. You're saying the number of solutions is 0, right? So if somebody says how many solutions are here, you're going to say infinitely many solutions, like that. Or if they say what is the number of solutions here, then you could say infinity, right? So we can summarize our understanding of linear equations in one variable in the following way. So linear equations in one variable fall into one of three categories. One is the most familiar type we're used to, where we only get one solution. So, such as x plus 2 equals 5, right? That gives us just x equals 3. Notice that these equations are true sometimes and false at others. For example, this equation is true if x is 3 and is false otherwise, right? So we say these equations are conditionals because their truth or falseness depends on certain conditions being met, right? So the most common type of linear equation that you're used to are called conditionals. They lead to only one solution, and they're the ones that you often encounter. We have then also the ones where you have no solution at all, right? The ones that are impossible, the ones we just saw. We call those contradictions. Remember that these look kind of like the one we just talked about, x equals x plus 1. And these obviously have no solution. You try to solve these and you will reach a contradiction. So therefore, you know you have no solution. And finally, you have the kind where every real number is a solution. Those are called identities, right? Equations such as x plus 1 equals x plus 1, right? Something like that. Any real number would make that true. So these will have infinitely many solutions, right? So here for this first group, the conditionals, the number of solutions is 1. For the middle group, the contradictions, the number of solutions is 0. For the last group, the number of solutions is infinity. Okay, so there are infinitely many solutions. All right, so that's a simple categorization of all linear equations in one variable. So as a final word in this matter, remember, the only number that you can multiply the terms of an expression with is 1. Notice in this case, we're multiplying by 3 over 3, which is 1, and the next term we're multiplying by 5 over 5, which is 1, because the terms can be multiplied by 1 without actually changing the expression, right? But the number that you can multiply both sides of an equation with is any number that you like other than 0, right? Of course, you don't want to multiply by 0 because that'll just wipe out the equation. Otherwise, it doesn't make, it's not necessarily wrong, but it's useless. So here, we notice that we can multiply both sides by any non-zero number. So we pick the number cleverly as the LCD, and that'll clear all the fractions for us, okay? One of the ways we can solve an equation is by using graphing. And we can do so by taking an equation like this, setting each side equal to y. We've seen this before in our previous video. And then we get these two equations, we graph them, and the point of intersection is the one we're going to be interested in, because for that x value, both this expression and this expression are going to have the same output, -3. So, but the x value that makes that equal output possible is 4. So the number of interest for us once we find the point of intersection is actually the x coordinate, right? So once we see that, we can say that the solution is x equals 4. And we can write it as a solution set in this way. All right. If you recall, we can also use tables if they have enough information in them, right? So notice here we are given tables for two expressions. One is 2x minus 5, the other one is negative 4x plus 13. And of course, that expression is what we're calling y in this side, and that's what we're calling y in this table. So notice that the x values that we are using as inputs for the expression are the same x values, 0 through 4, right? And we notice that once we get to the input 3, both those expressions happen to crank out the same output, right? So this tells us that the x value that makes both these expressions become equal is x equals 3. So from that we conclude that the solution here is x equals 3. So we write s equals like that, okay? Notice, of course, that's super easy to check. Plug in 3, you get 2 times 3 is 6, minus 5 is 1. Here you get negative 4 times 3 is negative 12, plus 13, that's also 1, right? So you can see how 3 is indeed a solution of this equation. The last thing we're going to do is look at some input and output pairs for a function. Remember, we can also write a linear equation in the form of a function here. This is not multiplication symbol here. This is functional notation. The proper way of reading it is f of x equals 3 half x minus 1, which basically means f is pretty much a machine, right? You give it an input x, out comes 3 half times that number minus 1, right? So it's an input output pair. So now we want to know what the output of this function will be if the input is 4. So we want to know if we plug in 4, what comes out. Of course, we know that all that's going to happen is we're going to take what we have x and we're going to replace it with 4. So we're going to get 3 half times 4 minus 1, like so, right? So we're going to get 3 halves times 4. We can write it as 4 over 1 if we like, to make it look like a fraction. And then minus 1, right? Of course, now we can do any kind of cross-canceling that's possible, like so, within this multiplication, of course, only not across this minus sign. You only cross-cancel here. You would never cross-cancel across a minus or a plus. But as long as you're multiplying two fractions, within that multiplication, it's perfectly okay to cross-cancel. And so we end up with 3 times 2, which is 6, minus 1, which is 5, okay? Now, the other question that's being asked here is very different. This time, they gave you an input 4, and they asked you for the output, f of 4. This time, they're giving you the output, and they want to know what input would give you that output, right? So where you're going to substitute that negative 4 is not for x, but rather for all of f of x, right? So we're going to get negative 4 equals 3 half x minus 1. And now we need to just simply solve that for x. Let me write that larger because we're going to be multiplying. So negative 4 equals 3 half x minus 1. Now, notice the common denominator. It's an equation, so we can get rid of the fractions or clear them by multiplying by the LCD. And the LCD is just 2, right? So we're just going to multiply both sides by 2. Don't forget, because of distribution, each term needs to get multiplied by 2. So we end up with 2, and of course, it's like this. You have to be careful. 2 times negative 4 is negative 8. Over here, we have the 2's canceling out. So we just get 3x minus 1 times 2, which is 2. So now we're going to go ahead and move the -2 to the other side, so it becomes +2. So we get -6 equals 3x. Now simply divide both sides by 3, and we end up with x equals -2. So what number is it that we can use as x so that once we plug it in, we end up with -4? That number would be -2. Okay, try it. Go ahead and find f of -2, right? See, you just go 3/2 times -2 minus 1. The 2's cancel out, so we get -3 minus 1, which is -4. You see? So this time we were given the input 4, asked for the output f of 4. Here we're given the output -4, so we're given a number from this side, and we're asked what's the input? What's the input on this side that if we plug it into this function will give us that output? That's what we're doing. Okay, so as the last problem we're going to look at, we're going to use a model to make an estimate. In fact, first we're going to actually create the model. The sales of musical instruments were 6.39 million in 2010, and then they went down from there by 0.28 million per year until 2014. We want to know which year resulted in a sales of 5.3 million, right? So if we're going to look at a table situation, notice we would have like T and maybe S for sales, right? So in other words, T would be our independent variable or explanatory variable. S would be the dependent variable or the response variable. So this one, remember, the independent or explanatory. This one would be the dependent variable or the response variable. Now, we are actually not going to need to set up a table, even though we could, like for example, if T is the number of years since 2010, right? So for example, in the year 0, which means 2010 itself, the sales were what? 6.39, right? The next year, maybe 1 year later, you would just subtract the 0.28 from that, right? So in other words, you would do this calculation. You would just do 6.39 minus 0.28, right? And we get 6.11, etc. Notice we can keep doing that, right? Then for the next year, if you were 2 years later, you would do the same thing. You would just take that 6.11 and again reduce it by 0.28 million. So this time you'd get 5.83. Remember, T is in years and this one is in millions of dollars, right? So now we could, however, set this equation up very simply by just reasoning. So we're going to say, look, how did the sales look? Well, we started with what? With 6.39, right, million. Then we reduced it by how much? By 0.28 million. You got to be very careful to use the same units here, right? So if this is in millions, this has to be in millions too. So minus 0.28 and then per year, right? So we're just going to multiply by T like that. So see how it makes sense here? For the first year, this is just, the first result is just 6.39 minus 0.28 times 0, right? The second result is 6.39 minus 0.28 times 1, right? This one is 6.39 minus 0.28 times 2, etc. So this is a perfectly good model for what we're dealing with, right? Now, sometimes if people want to put this in linear format, this model, they'll put this first. So you may see it in this form, where we want to put it in the y equals mx plus b format. So we'll put negative 0.28t first, and then plus 6.39, right? Like so. Okay, so let's look at what we're trying to find, the year in which, right? So we're looking for a t-value. We basically want to know when this side, in other words, the response variable, has a value of 5.3. So what we're plugging 5.3 for is the sales. So in this equation, we're going to plug in 5.3 equals 6.39 minus 0.28t, right? So notice that I can move the negative 0.28t to the other side. It becomes 0.28t, and I'm going to move the 5.3 to the other side. 6.39 is not moving, doesn't change signs. So we get that, right? So we get 0.28t equals, now we just need to do 6.39 minus 5.3. All right, so 6.39 minus 5.3, we get 1.09. So now we need to go ahead and divide both sides by 0.28. So we get t equals 1.09 divided by 0.28. All right, so 1.09 divided by 0.28. So we get, oh, I lost my calculator, 3.89 approximately. So if we're going to go ahead and round that to the nearest whole number, that's approximately 4, right? So notice that t is the number of years since 2010, right? So the year will be 2010 plus 4, which is 2014. So that's the year, according to the model, when the sales should reach around 5.3 million. Okay, so very, very simple. You're given an output, ask for the input, right? So you're given a sales amount, asked for the corresponding time. But don't be happy with just finding time, because they asked you which year. So be very careful. If they said how many years does it take for this to happen, you could have just said 4 years. But they didn't. They said estimate the year in which. And remember, t is the number of years since a reference year, here being 2010. So once you get t, you just add it to 2010, and that'll tell you the year in which you can expect sales to drop to 5.3 million from the initial 6.39 million. All right, that pretty much brings our lesson to a wrap. Next, we'll look at a few examples of the type of problem you'll encounter on homework, and then we'll call it the day for this video. All right, so here we have a problem containing fractions. We could take the classic approach of just multiplying both sides by 8 to clear the fractions, or we could recognize it as a proportion and cross multiply. In this case, they work out pretty much identically. So let's just go ahead and multiply both sides by 8 in this case, which is the LCD. So we have 5 times x minus 3 over 8 equals negative 2x. remember, you can't just say to yourself, oh, I only need to multiply this side by 8 because that'll clear the fraction, I can move on. No, you can't do that, right? Because it's an equation. So anything you do to the left side, you have to do to the right side as well. That's the only way it'll stay balanced, right? And it'll stay equivalent to the original equation. Remember, you want to solve an equation that is simpler but equivalent to the one you started with, meaning it has the same solutions. All right, so now we notice that the 8s will clear out here, and we end up with 5 times x minus 3 equals negative 16x. And so 5x minus 15 equals negative 16x. We'll go ahead and keep the 5x here, bring the negative 16x over, it becomes plus 16x. Move the negative 15 to the other side, and it becomes positive 15 on that side. So we get 31x equals, that's 21x actually, equals 15, right? So now all we have to do is divide both sides by 21. So we end up with x, that's 21. So we end up with x equals 15 over 21. Now, you never want to type that in as the answer because that's not fully reduced. You always want to put in the most reduced form of any fraction. So notice that 3 goes into 15 5 times, and it goes into 21 7 times, right? So the answer we will type in is x equals 5/7. But let's go ahead and do a quick check using our calculator to see if this is in fact a good solution for this problem. So let's see what we have. Let me move it over here. All right, so we're going to type in, we're going to start with a fraction. So this is the best, easiest way to deal with this. Start with a fraction, then notice it puts the cursor on in the numerator position. Now we're going to put in 5 times. For x, I'm going to type in 7. Let's see, what do we have? 5 over 7, right? Let me write that over here. 5 over 7, right? All right. So we're going to type in 5 over 7, just like that. And then minus 3, and now we're going to close the parentheses. That's all we have on the top. So then we're going to hit the down cursor. That puts the cursor in the right position to type in 8. All right, so that's what we get when we substitute 5/7 into the left side of this equation. Now the right side also has a variable in it, so we need to now calculate that using the variable, right? The value of 5/7 for x. So we get negative 2 times 5/7. And we notice that after doing so, we get exactly the same output. That means plug in 5/7 into this equation makes it true because it makes both sides exactly that same value, right? So we are done, and we have shown that this solution is a valid one. We could also turn that into a fraction, and we notice that in that case we get negative 10/7 on both sides, okay? Which of course makes sense. Negative 2 times 5/7 is what? Negative 10/7. A great practice for you would be to do this manually by hand, okay? To make this video not take forever, we don't always check completely, but the check part is actually some very good practice for you. Okay, here's one that I would really like you to recognize as a proportion and handle it in that way, because that's the nicest, fastest way of handling it. If you recall, An algebraic proportion looks like this. You have one fraction equals another fraction, right? And when that's the case, you know that you can always do what's called cross multiply, right? So you end up with AD equals BC. Now, when we have 9x plus 7 over 2 equals 7x minus 9 over 3, we are exactly in this form. One fraction, look at the number of fraction lines, basically, only one, right? So one fraction equals one fraction. So we can use this. So now we're going to cross multiply like that. And we're going to get 3 times 9x plus 7 equals 2 times 7x minus 9. So now we get 27x plus 21 equals 14x minus 18. Let's get the x's on the left side. So 27x minus 14x. Remember, change sides, change signs. Okay? On the other side, negative 18 doesn't move, so it doesn't change signs. But 21 moves from here there to there, so it becomes negative. So negative 21. So we get 13 actually, right? 27 minus 14. 13x equals negative 39. Now we're just going to divide both sides by 13. So we get x equals negative 3. And this is really, really simple. So let's just go ahead and quickly check it together. So here's a check. 9 times negative 3 plus 7. Remember, we're just taking negative 3 and we're plugging it in for x in the original equation. Every place we see x, right? So over 2, we want to know if that's equal to 7 times negative 3 minus 9 over 3. Now, right here, we have negative 27 plus 7, right? That's negative 20 over 2. We want to know, over here, we have negative 21 minus 9. So that's negative 30 over 3. So negative 20 over 2 is negative 10, and negative 30 over 3 is also negative 10. So we have reached a true statement, an identity, which is always true. So therefore, we have shown that plug in negative 3 makes this equation true, like that. Okay, so therefore it's a solution. So that's how you would handle a proportion like that, the fastest way. You could, of course, multiply both sides by 6, clear the fractions and all that, right? But this cross multiplication is too beautiful not to apply. All right, so remember that cross multiplication only works when you have one fraction equals one fraction. We don't have that here, right? We have more than one fraction on this side, or more than one term, right? So here we just do the classic approach, find the LCD for both sides, right? And of course, if you look at the prime factorization of 4, that's just 2, 2, 2, 1, right? For 5, that's a prime number, so it's just 5, 1. For 20, we get 2, 10, 2, 5, 5, 1. So 20 is 2 squared times 5. 5 is just 5. And 4 is 2 squared. So if you take the highest power of 2, which is 2 squared, and multiply it by the highest power of 5 that you see, which is just 5, you end up with what? 20. You may have known that, and that's fine, except this works even when the numbers down here are really large. So it's always good to know the procedure. All right, so we're going to multiply both sides of this equation, 3m minus 2 over 4. minus 2m plus 1 over 5 equals 2 over 20. So we're going to multiply both sides by 20. We keep in mind that we have to distribute, right? And the same like that, okay? So now we notice that 4 goes into 25 times, 5 goes into 24 times, and 20s cancel out, right? So now we carefully write down what's left. Don't multiply and distribute already, okay? Take your time with these. Just write down what's left. 5 times 3m minus 2 minus 4 times 2m plus 1 equals just 2, right? So we get 15m minus 10 minus 8m minus 4 equals 2. It goes without saying that you should always try these problems on your own with the video paused before you come back to check to see if you did it correctly. That's the way you learn mathematics, right? By doing it. All right, so we get, now we're going to simplify the left side by combining the like terms. These two give us 7m, those two, negative 10 and negative 4, give us negative 14 equals 2. So we get 7m equals 2 plus 14 after we add 14 to both sides or move negative 14 to the other side, same thing. So we get 7m equals 16. So divide both sides by 7 and we get m equals 16 over 7. Let's go ahead and check that quickly. All right, so we'll start with the fraction. On the top, we'll put in 3 times, I'm just going to use parentheses instead of times, 16 over 7. We're going to have to hit the right arrow. And again, until now, we close the parentheses and we put minus 2, right? And now we hit the down arrow and we put in 4. Now we're gonna, come out of that fraction, so we need to hit the right arrow and then minus. Again, we hit the division sign to create a fraction, and now we put 2 parentheses 16 over 7. Hit the right arrow, close the parentheses, then hit the down arrow and type in 5. And we get this. Let's go ahead and turn it into a fraction. Okay, now we have to make sure that this agrees with what we have on the other side. So let's see, we see a discrepancy. Okay, I noticed what happened here. Notice there was a +1 that we didn't put in. So it's good that you're seeing all the ways you have to be careful, right? So here, this is what I do to make sure basically I have the right input. After I type it in, I usually take a few seconds to go back and make sure that I've put in everything, right? And when I did that just now, I realized there was a +1 that I had left out, so I added it. Okay, so always take a few seconds to double check. It takes you 5 seconds, but it'll save you 5 points on the test, right? So then that's that. Now on the other side, we don't have that, but look what we have. We have 2 over 20. Go ahead and type it in and hit enter. Notice it'll simplify it for you. And if you put it in fractional form, now you see we have exactly the same output when the input is 16 over 7, and we get the same thing on both sides of this equation, 1/10. So we know it's a correct solution, and that's that. So we write S equals 16 over 7. Modern mathematics is all about sets. It uses set notation pretty much everywhere. So this is the set notation describing all the solutions of this equation. Here's a problem containing decimals in it. Now, when it comes to decimals, you could just deal with decimals if you're comfortable enough with them, or just like we did with fractions, you could also clear them. Let me show you how to clear them. 5.11x minus 6.24 equals 2.74x plus 9.85. Notice that I'm going to go through and I'm going to look at each term and find out what power of 10 I need to multiply that term by to clear the decimal, right? I noticed this one, the decimal would be cleared if I multiply it by 100, right? Because multiplying by 100 moves the decimal 2 to the right. Same with this, same for that one, and also for that one. So I notice that 100 would be the largest number I need to clear all the decimals. Now, if one of them, let's say this one was 9.853, right? Then I would need 1,000 to clear that one. And then I would multiply both sides by 1,000, right? So you find out what each term needs and get the largest of those values that are needed and multiply both sides by just that number. So in this case, it would just be 100. So now I'm just going to multiply both sides by 100. So I'm just going to put them right above like this for simplicity. So I get 100 times that minus 100 times that, right, equals 100 times that, and then 100 times that. So basically, notice I'm just multiplying both sides by 100. Let me bring that back actually. Okay, so notice we're multiplying both sides of this equation, this original equation which I reproduced down here, by 100 is what we're doing, right? And then we're distributing, right? So each term is basically going to get hit by 100. So that's the safest way to fly. When you multiply both sides of an equation by some number, make sure that number gets multiplied by each term because of distribution, okay? So notice that we end up with 511x, because that's what 5.11 times 100 is. Multiplying by 100 moves the decimal 2 to the right, right? Minus 624 equals 274x plus 985. So now we have an equivalent equation, meaning an equation with the same solution that has no decimals in it. That's the nice thing about the multiplication property of equality, right? It helps you clear fractions as well as decimals. And now we're going to get the x's on one side. So 511x minus 274x equals 985 plus, remember, you're moving negative 624 to the other side, or in other words, adding 624 to both sides. So it becomes plus 624 on the other side. Now we do 511 minus 274. All right, so 511 minus 274, we get 237. On the other side, we need to do 985 plus 624. Okay, we need to clear that. 985 plus 624. Let me make sure. Yeah, that's right. All right, so we get 1609. So now we're just gonna divide both sides by 237. We get x equals 1609 divided by 237. So we get that. Now, we need to go back and see what kind of instructions they'd given us, right? Type an integer or decimal rounded to 2 places. So they don't say fraction, so we're just going to give the answer in decimal form, right? So now we bring back our calculator. No, that's the wrong one. That's that. And then here's the calculator. So to 2 decimal places, that will become 6.79. So we say approximately 6.79. Again, that's a decimal to 2 places. All right. So that's one way of dealing with decimals, by clearing the decimals altogether. Or remember, if you're comfortable enough with decimals, you don't have to do that. You could just work with them. Watch. It's a lot faster if you just work with them, if you're comfortable enough with them. So given that, I mean, we use calculators for the basic computations anyway, it's pretty straightforward to do so. But I did want you to see how you can indeed clear them, right? So if you're just going to work with decimals, you're just going to get the x's on one side, and you're going to get the numbers, the constants, on the other side. So now we need to do 5.11. Let me move this to the other side now. So let's clear all this. All right, so now we're going to do 5.11 minus 2.74. That's 508.2. What happened? We put 511, so 5.11. All right, so 2.37. You always want to have common sense as your companion. So 2.37. So 2.37x equals. Now on the other side, we need to do 9. Okay. 9.85 plus 6.24. So that's 16.09. Now we just divide both sides by 2.37. So we get 16.09 divided by 2.37. And we end up with the same answer, of course, approximately 6.79. So you have a choice. You can clear decimals or not, okay? Okay, so for a problem like this one, be very careful not to clear the fractions, because this is not an equation, it's an expression. With an expression, you may not clear fractions. You may combine fractions by making them alike, but you cannot clear them. So let's see how we would approach that. So we have 5x over 2 minus 1/3 minus 1/6 plus 11x over 4. So the first thing we'll do is we'll put the like terms next to each other. So we put 5x over 2 and 11x over 4 next to each other. Remember, if you have terms like this, you can move them around as much as you want, as long as each term maintains its sign, right? So we can say, for example, let's start with the negative. So we can go negative b minus d plus a plus c, right? Notice all the terms have maintained their signs. The sign of a term is on its left, right? So, or we could do all positives first. So we can do a plus c minus b minus d. Or we could do reverse alphabetic, so negative d plus C minus B plus A. There are many different possibilities, right? But notice that each term maintains its sign, right? So next, we're going to put negative 1/3 minus 1/6. We're putting the constants next to each other. Now, for these two, right, fractions, the LCD is 4. So we write a 4 here. And we go ahead and make the 2 into 4 by multiplying by 2. Which means, of course, we have to multiply the top by 2. This is already 4. We don't need to do anything. So we end up with 10x plus 11x, right? Now, plus, you may say, but that's a minus. That's okay, but you can always write negative 1/3 as plus negative 1/3, right? This will make it less likely that you'll make a mistake if you do it this way. So what is the LCD now? It's 6, right? So for 3, we need to multiply it by 2. And of course, don't forget the top. For 6, you already have 6. You don't need to do anything. So now on the top, you have negative 2 minus 1, like that. You see? So we end up with 21x over 4 plus negative 3 over 6. I notice that I can reduce that to 1 and 2. And of course, I'll put the final result as in the simplest possible form, which is 21 over x over 2. And I'll multiply that positive and negative to just get a minus 1/2. Okay? Oh, my quick check just showed me I miswrote this. That's actually 21x over 4. And that's it. You go ahead and leave it like that. Now, sometimes you may, if you're like using a traditional textbook, you may see this answer given in this form. That's because, remember, that's also okay, because look, you have 21x over 4 minus 1 over 2. Notice the LCD is 4, so you can multiply this by 2 and that by 2, and then you'll end up with 21x over 4 minus 2 over 4. And of course, because both of those denominators are the same now, you can just write them once and combine the numerators, right? So you may see the answer in that form as well. But for our purposes, you can just type that in, okay? And that's how you would simplify this expression. Notice we're not solving here. That's why the final result is not a number. It's a what? It's an expression, because we're simplifying an expression. Okay, in this problem, we're going to solve this equation using graphing. So what we're going to do is we're going to call this, let me bring that back. We'll go back to it in a minute. So we're going to call this one a y. Let me copy these and paste it into the other. Here we go, that's better. Okay, so basically what we're going to do is we're going to call this one y, and we're also going to call this one y in this way. We're going to graph two linear equations. Y equals negative 1/3 x plus 5/3, and y equals 3/2 x plus 7/2. And then we're going to see where those two lines that represent these equations, okay, I wrote this incorrectly, 3/2 x. All right, not 3 over x2. So 3/2 x plus 7/2. So we're going to graph both equations and see where the lines meet. So let me bring back our calculator. This time you want to make sure you're in graphing mode. All right, so now we're going to type in the first equation. So we have y equals negative 1/3 Make sure you get out of the denominator position by hitting the right arrow. X plus 5/3. And, oh, what did I do? Let's see, I put infinity. Let's backspace a little bit, and there. So negative 1/3 x, so I'm just always going to double check, right? Negative 1/3 x plus 5/3, right? So that's good. And then now we're going to type in the other equation, y equals 3/2. I don't know why it keeps hitting. I guess it's, let me see. Yeah, if you, for some reason, I don't know, maybe you do. So 3/2 x plus 7/2, right? So there's the graph of the two. So we know we're going to be looking for this point right there, the point of intersection. And of course, remember, it's the x value that's going to give you the same output for both sides, right? So the y value will be 2. In other words, these expressions will have a value of 2 whenever the x value is -1. So the solution here will be x equals -1. Like so. Okay? All right, so here's a different kind of problem related to graphing. Notice that they're giving us the graph of this equation on the right. I expanded it. It's given to you in a smaller form. You just make it zoom up a little bit to show you better. Zoom in, actually. And you want to use this graph to solve this equation. That's all you're given, this graph, right? You don't need to use a calculator. You don't need anything. You just look at this graph to solve it. And notice each point on this line is going to have the form xy, right? So the x value, of course, is the input. The y value will, in fact, have this form, -1/2 x plus 9/2, right? So all you have to do is look where the y value is 1 on this point. Look, in other words, locate the point on this line which corresponds to y equals 1, right? And see what x value is paired with that. So when you do that, you realize it's the x value right here, 7, which is going to give you the output 1, because the point 1, 7 is on the graph of this line, right? So therefore, what x value is it that gave us that y value? Obviously, actually, that's right. I wrote this backwards. It's 7, 1, right? So notice that the x value that gives the output 1 is 7. Now, it also makes sense if you check it. Look, -1/2 times 7 plus 9/2. We want to know if that's equal to 1, right? That's -7/2 plus 9/2. We want to know if that's 1. 2/2, is that 1? And of course, 1 equals 1, so it makes it true. See? So, the mind, you know how it has the tendency to, when you have a fraction like 3/24, it likes whole numbers, so it may say 8. It kind of also expects a bigger value in the x position for some reason. At least my mind does. So be careful with that, your mind playing that trick on you, okay? Here, the x value is 7 and the y value is 1, okay? So, so we can see the solution is going to be the x coordinate, which is 7. So the solution here would be x equals 7. We put it in our solution set, like so, and we're done. In this problem, they give us a table of values for this function, y equals 8x minus 6. Look, When, for example, when x is -3, you get 8 times -3, which is -24, minus 6, which is what? -30. When x is 0, for example, you get 8 times 0 minus 6, or 0 minus 6, or -6 for y. You see that? 0, -6. When x is 2, you would get 8 times 2, which is 16, minus 6, which is 10, etc. Right? Now they want you to use this to solve this equation. In other words, you want to know in this table for what input is the output, which is given over here, equal to 10, right? So you want to know when 8x minus 6 equals 10, and of course you can see what input corresponds to an output of 10? 2. See? 2 goes with 10. All right. So we have x equals 2. And of course you can check that super quickly. 8 times 2 is 16, minus 6 is what? 10. This is using a table to solve an equation. Not the most, efficient way. I mean, who wants to sit there and waste time making a table and then finding that? However, if the table is available, it's nice to be able to detect the solution from it. So it's for those situations. It's not something you want to sit there and do, right? You don't want to sit there and do a table just so you can find the solution. No. You see an equation, you want to solve it in an intelligent algebraic way. However, sometimes the table is available, and when you look at it, you should be able to see make those connections. That's the purpose of this kind of exercise. Not that we're interested in you sitting there and solving equations by what? Making tables. Same with graphing, right? It's very inefficient to want to sit there and graph lines and then find the point of intersection in order to solve an equation, right? No, but we want you to make the connection and understand the geometric relationship to the situation, and that's why we're getting you to do these problems. All right, in this one, we're interested in finding the value of x for which f of x, which is this function, is 8. So it's very simple. We just put f of x equals -2x plus 9, and we want to know what value of x would make this side 8. So just replace f of x with 8. And that'll tell you what x value. Just solve this. Let's bring the -2x to this side to make it +2x. And let's move the 8 to the other side to make it -8. So we get 2x equals 1, or x equals what? 1/2. You have some extra time on your hand. You want to make sure this makes sense. Just evaluate f of 1/2 and see if it'll give you 8. Look, f of 1/2, wherever you see x, plug in 1/2 instead, right? So -2 times 1/2 plus 9. So that's -1 plus 9, which is 8. So f of 1/2 is indeed 8. Isn't that what you were trying to find? You were trying to find the input whose output is 8, right? Look, here's the input, and the output of this function for that input is 8. So there, we found it in the first part anyway. Okay? This is more of it. This is not more of, this is exactly a check. Okay, in this problem, we know that in 2009, the average per person annual consumption of cheese was 31.3 pounds, which was up 11.8% from 2000. What was the average per person annual consumption of cheese in 2000? So that's our unknown, right? We don't know what the consumption was in 2000. So let x be the average per person annual cheese consumption, right? Amount, of course, right? Now, but we do know that this 31.3 pounds which referred to the year 2009, was whatever x was plus 11.8% of whatever x was, right? This is how you handle when they say up by this percentage, right? And that is what ended up being 31.3. So we don't know what the consumption was in 2000, right? But we know that whatever it was, if we add 11.8% of itself to it, we should get the new amount which corresponded to 2009. Okay? So to solve this, we simply have to take that number right there and make it usable in an equation. So let's do that on the side. 11.8%, that means 11.8 over 100, right? Which means move the decimal 2 to the left, so it's 0.118. So this is the usable form in equations. So we get x plus 0.118x equals 31.3. So x equals 31.3 minus, actually, correct that. These two are like terms. We need to combine them. It's getting a little late here. So 1x right here plus 0.118x. So we get what? We get 1.118x equals 31.3. So now all we have to do is divide both sides by 1.118. So we get 31.3 over 1.118. So now we'll use our calculator for that. So 31.3 divided by 1.118. Okay, and we get, let's see what kind of instructions they have for us. Rounded to one decimal place as needed. So if you round to the nearest one decimal point, right, you're actually going to have to look to the right, and that's a 9. So you have to round up, so you get, actually this becomes a 10 and that becomes an 8, right? So that becomes 0, that becomes 8. So we get approximately 28. Let's bring back our sheet. So we get approximately 28. If you want to show that you rounded properly, you can put the 0.0 pounds. So in 2000, it was about this much, and it went up by 11.8%, and it is now 31.3% in 2000. Well, it was 31.3% in 2009. Okay, that should be enough to get you through this set. So make sure you get things done on time, and be safe. I'll see you in the next video.